When we look for life in the universe, we have a very specific template in mind. We expect to find carbon-based organic matter that required billions of years of slow, lucky evolution to develop. That timeline creates a problem when we look out into the vast, empty stretches of space. Most of the cosmos is just a freezing vacuum, filled with scattered dust grains and ionized gas known as plasma. The math simply doesn't favor the rapid, random assembly of complex organic molecules in an environment like that. The universe is old, but perhaps not old enough for chance alone to build biological cells in the deep freeze of space. But recently, physicists observing that seemingly dead space dust noticed something strange. The particles were spontaneously organizing themselves into highly complex patterns called plasma crystals. It forces us to ask an uncomfortable question. If we take our strict biological checklist for what defines a living organism and apply it to this space dust, we might find that inorganic life is already out there. In a vacuum, solid dust grains bombarded by electrons quickly acquire a negative electrical charge. Basic physics dictates that these identically charged particles should violently repel one another. But space isn't a perfect vacuum. These grains sit inside a plasma field, meaning they are continuously hit by a flowing stream of surrounding energy. That constant inward flow triggers a phenomenon known as plasma overscreening. The incoming plasma creates a concentrated pocket of positive charge around the dust grain, which acts like a tiny attractive well. This simulation tracks this process. We start with a chaotic red cluster. As the attractive well overrides repulsion, grains clump into the organized blue spherical structure on the right. To stay stable, this blue core must continuously feed on surrounding plasma. We know these structures form distinct, sharp boundaries in reality, too. Astronauts aboard the International Space Station have conducted microgravity experiments that confirm these dust crystals isolate themselves from the empty space around them. Consuming an external energy source to maintain a physical boundary is the exact definition of metabolism. The dust passes the first test. In these structural diagrams, the red and green spheres stretch out under slight asymmetry. They self-organize into double-winding helical structures, resembling DNA. The graph on the right maps a bifurcation, a critical threshold where the helix snaps into a wider diameter and new rotational angle. Once the structure shifts, it locks in place. The physical arrangement of the dust grains acts as a rigid, lasting memory mark. Storing data in a permanent physical format means this inorganic structure possesses a genetic record. But a genetic record is useless unless it can be passed down. How does a cloud of charged dust, with no cellular machinery, manage to clone itself? These colored convection fields reveal the mechanics. The helix's shifts generate intense electrical gradients, whipping surrounding plasma into swirling storms. In the bottom schematic, vortex rings circulate between two helices. This storm acts as a transmission field, radiating the original structure's data outward. When a second unbifurcated helix floats through that storm, the intense vortex physically forces the new dust particles to bend. They snap into the exact structural pattern of the original. It is frictionless structural copying. The first helix passes on its acquired traits to the second, achieving a literal form of inorganic cloning: autonomy, metabolism, memory, and reproduction. By satisfying every requirement on the checklist, these self-organizing structures qualify as a form of living matter. Because these interactions are driven by high-frequency plasma fluctuations rather than slow chemical reactions, this inorganic life evolves at a rate exponentially faster than carbon-based organisms. Given that immense speed, it raises a difficult question. Did these fast-evolving dust structures form first and eventually seed the biology we recognize today? It forces us to rethink our SETI programs entirely. We spend our time looking for water on distant planets, but living matter might be floating in the starry dust clouds right above our heads. If you want to keep exploring the edges of science with us, hit the like button and subscribe to the channel. And a special thanks to Synestex Systems LLC and founder Shane Persinger for supporting this deep dive.